Welcome to this explainer. Today, we're going to completely demystify the foundational design and step-by-step installation of jacketed piping systems. If you're at all involved in chemical or industrial plant design, this is going to be incredibly valuable for you. We'll be looking closely at the strict engineering guidelines that dictate exactly how these complex systems are put together to ensure efficiency, safety, and structural integrity. And really, why does this matter so much? Well, because a failure in one of these thermal systems can literally shut down a multi-million-dollar plant.
So let's just dive straight into this by asking the fundamental engineering question. How do we actually prevent localized freezing and totally eliminate those dreaded hot or cold spots in industrial piping? When you have highly sensitive process fluids moving through a facility, standard insulation just doesn't cut it. You need a system that actively manages temperature, delivering heat or cooling exactly where it's needed every single time without fail.
Here is our roadmap for today. We'll cover 1. The basics of jacketed piping, 2. Essential system components, 3. Flange configurations, 4. Flow directions and limitations, and 5. The branch installation procedure.
Section 1. Basics of jacketed piping.
The whole pipe-within-a-pipe concept is brilliantly simple, but it is highly effective for thermal control. The system is fundamentally made of 2 pipes. The inner pipe, which we call the core, carries your actual process fluid. Then you have the outer pipe, known as the jacket, which acts as a conduit for a totally separate fluid that is explicitly there to either heat or cool that inner core.
What's fascinating is how much jacketed piping outperforms standard tracing methods for efficient heat transfer. Think about conventional tracing for a second. Heat is usually applied along a single line or wrapped around the pipe like a wire. Unfortunately, that often leads to really uneven heat transfer and localized freezing. Jacketed piping solves this completely by enveloping the entire circumference of the core pipe, giving you beautifully uniform heat input and far superior, much tighter temperature control. Depending on your specific process needs, the outer jacket can utilize a really wide variety of liquid or vapor media. Let's say you need to keep a highly viscous fluid flowing. Think something as thick as industrial molasses. Well, you might pump steam, hot water, or a thermic fluid like Dowtherm right through that jacket. On the flip side, if you're managing a highly reactive process that absolutely has to stay cold, chilled water or chilled brine works perfectly.
Section 2. Essential System Components.
Now, there is a very precise engineering relationship between the core sizes, jacket sizes, and the required distance between the internal spacers. For instance, a 50mm or 2-inch core requires an 80mm jacket, and you have to place spacers every 3 meters. Bump that core size up to 100mm, and suddenly you need a 150mm jacket with your spacer interval extending out to 4.5 meters. These specific pairings are crucial because they ensure optimal flow volume for the heating or cooling medium while maintaining strict structural stability.
The absolutely crucial point here is that the inner core pipe has to be perfectly centered and structurally supported within the jacket. To pull this off, spacers are welded directly to the core pipe at exactly 120-degree intervals around its circumference. And here is a vital design rule you cannot ignore. The spacer material must always be the exact same material as the core pipe itself. Why? Because mixing metals in there could lead to disastrous galvanic corrosion or structural failure deep inside the system where you can't even see it.
Bends in the system get a little tricky, so these are your rigid rules of the road for butt-welded elbows. Because the jacket has to fit perfectly over the core's bend, the core elbows must be a long radius type, specifically 1.5 times the diameter. Meanwhile, the outer jacket elbows use a short radius of exactly 1.0 times the diameter. And honestly, if things get too incredibly tight during assembly, that outer jacket elbow can actually be split in half to fit perfectly over the core bend.
You'll find that jackets are intentionally broken up into heated sections, usually using blanks. Jumpers act as the vital little bridges to carry the heating medium across those breaks. These jumper pipes ensure a continuous flow of your thermal medium without interruption, and the sizing is highly standardized based on what you're pumping. You'll use 15mm jumpers for steam and step up to slightly larger 20mm jumpers for hot water or thermic fluids.
Section 3. Flange configurations.
Usually your flange size is just going to perfectly match your core pipe. But what if you can't afford even a single inch of unjacketed pipe at the connection? That's where reducing type flanges become absolutely mandatory. In highly sensitive applications, you literally have to step down from the larger jacket size right down to the core size at the connection point. This ensures absolutely zero thermal loss at the joint itself.
We have to think about maintenance here. To allow for future teardowns, you must include flanges on those jumper connections we talked about earlier.
Think about it. If you just went ahead and welded a solid jumper pipe across a carefully flanged joint, you would completely defeat the purpose of having those flanges in the first place. By flanging the jumpers too, your maintenance crews can easily disconnect that thermal loop and unbolt the main pipe sections whenever they need to.
Section 4. Flow directions and limitations.
You just can't fight gravity, so gravity and thermodynamics will dictate our flow directions. Liquids must always enter at the bottom of the system to ensure proper venting. If you're using steam, you supply it at the top of the heated section. As it cools down and condenses into water, gravity naturally pulls it down to a steam trap at the lowest point. But for liquids, like chilled water or hot thermic fluid, you pump them in at the bottom and force them to flow upward to exit. This guarantees that any trapped air is pushed straight out the top, totally preventing air pockets that would ruin your heat transfer efficiency.
You can't just pump steam through a kilometer of pipe and pray it stays hot. Physics is going to humble you pretty fast. If your piping run exceeds specific maximum lengths, you are strictly required to design additional supply and return points. For steam, a single heated section really shouldn't exceed 25 meters. For water, you're allowed to stretch it slightly to 30 meters. But thermic fluids are highly dependent on the core size. You're dropping from a 15-meter max length on smaller pipes all the way down to just an 8-meter maximum run if you have a massive 200-millimeter core.
Finally, Section 5. Branch installation procedure.
Out in the field, sequence is quite literally everything. It's this very precise dance where you have to completely prioritize the inner core first. You always start by installing the main core pipe, and then you slide the main jacket section very loosely over it. Only then do you make your cut into the core pipe and weld your new core branch onto it. Once that critical inner connection is completely made, you then slide the outer jacket branch right over that newly attached core branch.
Now pay attention, because it is absolutely critical that the core welds are thoroughly examined and tested before the jacket is sealed around them. This is step 6, and I promise you it's non-negotiable. You must leak test that inner core weld while it is still exposed. If you skip step 6 and just weld the jacket closed, a leak in the core is going to be trapped, totally invisible, and unbelievably expensive to fix later on. Once the inner weld officially passes, you use the spacers to align everything perfectly, weld the jacket closed, weld the branch jacket, and finally perform a second, entirely separate leak test on the outer jacket weld.
As we start to wrap this up, please keep these overarching structural rules in mind, especially regarding the external pressure acting on the core pipe. Your main process fluid might be running at a really low pressure, but if your heating steam in the jacket is at high pressure, that core pipe is going to be intensely squeezed from the outside, so the core must be thick enough to handle that external pressure without just buckling inward. Also, for the designers out there, you aren't forced to support the core and jacket pipes at the exact same location along the run, which gives you some much-needed flexibility in your structural design.
I want to leave you with one final, incredibly vital thought on structural integrity. Have you actually accounted for thermal expansion? Think about it. If you pair a stainless steel core with a carbon steel jacket, they are going to expand at entirely different rates as they heat up. The resulting thermal forces are literally strong enough to bend solid steel and tear your beautiful system apart from the inside out. So, when you're designing your next system, ask yourself, are you just routing pipes or are you truly mastering the thermodynamics? Thanks so much for joining this explainer.